Quantum computers are cool, and I mean that in a very literal sense. In order to make use of quantum phenomena and to avoid calculation errors, the most advanced versions need to be kept as near as possible to absolute zero, aka 0 Kelvin, aka negative 273.15 degrees Celsius, aka the coldest temperature there is. Now though, researchers claim they've demonstrated hot qubits, which could be key to overcoming a major obstacle to scaling this technology up. The quantum computer is built around the quantum bit, or qubit. Like a classical bit in the computers you're used to seeing every day, a quantum bit can be used to represent a 1 or a 0 in logical operations. But unlike a classical bit, a single qubit can also be any combination of 1 and 0 simultaneously, thanks to the quantum phenomenon of superposition. Qubits can also take advantage of quantum entanglement. This allows a quantum computer composed of dozens of qubits to tackle certain problems in minutes, while ordinary supercomputers would take millennia. For quantum computers, the enemy is decoherence, when qubits interact with the environment and lose information. The colder and more isolated the qubit is, the less likely it is to flip to another quantum state when it's not supposed to. But well-isolated qubits are also difficult to keep cold, and the more qubits a computer has, the more heat the system generates. When you consider the fact that quantum computers that will tackle our biggest challenges, like precision drug making, will require millions of qubits, the problem becomes clear. We have to figure out how to keep these large quantum computers operating at an optimal temperature. There are two ways of approaching the problem. One is to improve cooling systems. The most sophisticated quantum computers we have now are based on superconductors and are kept cold with dilution refrigerators. Imagine basically a hideous steampunk chandelier and you're halfway there. Most that exist right now can keep fewer than 100 qubits cold enough to operate. So scaling up a dilution refrigerator to keep millions of qubits cold would be incredibly expensive, and still may not be capable of maintaining sufficient temperatures. And this is where two separate groups of researchers believe they've made a breakthrough. Rather than basing their qubits off superconductors, the scientists used nanoscale metal electrodes to confine electrons in silicon, in devices known as quantum dots. This allows them to operate at significantly hotter temperatures. How hot, you ask? A scorching 1.5 Kelvin. So, not exactly flip-flops weather, but at the atomic level, it's a huge difference. That's 15 times warmer than superconductor-based qubits can operate. A silicon basis has a few other advantages. We're already very experienced at making things out of silicon. It's the basis for all conventional computer chips, after all. So the researchers claim silicon-based qubits can be manufactured with foundries we have today. And get this, hot silicon qubits allow for the integration of conventional chips that can control the operations of the qubit. Normally, these conventional chips would get too hot to have them next to superconducting qubits, meaning they would have to be kept separate with long wires connecting them. But if the qubits can operate at higher temperatures, a silicon chip can be placed right next to them, and the overall size of the computer can be greatly reduced. Is this the breakthrough quantum computers need to push them from curious doohickeys to world-changing number crunchers? We'll only know when this 2-qubit proof of concept is scaled up. Until then, we'll keep tabs on all the other quantum computing breakthroughs until one of them finally establishes the quantum age. Another group of researchers recently discovered a more precise way of controlling qubits in silicon, and all it took was a series of fortunate accidents. Check out my other video on that story here.